I'd like to thank the organizer for giving me the opportunity to talk in this conference. So first, so the object that I want to, can you hear me? The object that I want to work with is as follows. So let us consider flat family of smooth projective varieties. Now I suppose I take a closed point in here and I look at the fiber. And I take a codimension P for some E, local complete intersection, subscheme. So we can, the cohomology group of Z0 will give us a Hodge class. Now what we want to ask is as follows. Under what properties of Z0 can I say the following? That when I deform X0 in this family, I would like to ask for all the deformations which keeps gamma naught a Hodge class, I would like to ask when does Z0 lift as a local complete intersection? For all infinitesimal. So I look at the infinitesimal picture first. Let's say X0 prime. This Hodge class lifts as a Hodge class if and only if Z0 lifts as a local complete intersection. So I'll make this statement precise. But basically this is a bit stronger. So this is just a slightly stronger question than the variational Hodge conjecture, but we are interested in something different. So the variational Hodge conjecture tells that gamma naught lifts as a Hodge class if and only if the cohomology class remains algebraic. So let me make this thing a bit more precise. So what do? I want to define the Hodge locus and look at the tangent space to the Hodge locus. So I first take the case when B is contractible. Then I have the Ersmann's theorem, which tells me that the family is trivial. Now this gives us a canonical isomorphism. So I pick any B in here. Now the question for whether a Hodge class remains a Hodge class can be made more precise. So the Hodge locus corresponding to this Hodge class is the analytic set I take all the points in B such that this object is Hodge. So the question now is that, so, okay, before I go to the question, so now in general, we can take any complex manifold B and glue. So I will call this locus, denote this locus by NL gamma naught. We can glue this over the whole of B. And this, the resulting object has a natural scheme structure. So I'm not going to go into the details of this, but it is coming from the Hodge filtration on the family, and you just need to look at the zero locus of certain holomorphic sections. So that way we can give a natural scheme structure to this. Now what we want to understand is what is the tangent space. So the tangent space comes in this way. So I have this family. So to this family, I first need to define the Kodaira-Spencer map. So the Kodaira-Spencer map comes from the following short exact sequence. Now here we get the Kodaira-Spencer map. Which is just the tangent space at this point in B, which is going to be the same as this object. And this has a natural map to the boundary map. And using this, we can now define the tangent space, which is, first we define the differential map. Now here I'm going to get the, so this object over here, here I want to put the information of the Hodge classes. So here I want to write HP of omega x naught p. And as you would guess that the way this map will be defined is first I take an element here, then I denote the Kodaira-Spencer by rho. So I take an element here, then I pass to an element here, and then I induce a cup product map over here, which means that here I will get an object in defined by where this thing is the cup product map. Now a standard theorem in Hodge theory tells us that the tangent space at this point to the Hodge locus is nothing other than the kernel of, so how I define this is where this is just comes from this definition just by adjunction. Now the question becomes that, now the question is, that for what properties of Z naught can I say that for all element in this tangent space to the Hodge locus, the corresponding infinitesimal deformation naught satisfies Z naught lifts as a local complete intersection in X naught. Now, a partial answer to this question has been there for some time due to Bloch, where he defines the, or rather he generalizes the concept of semiregularity map. So a partial answer to the question is due to Bloch. And what he says is this. So there is a semiregularity map. So I'm going to explain what is the semiregularity map. And this semiregularity map has the property, which has the property that if this thing is injective, then the answer to this question is true. Then we have a positive answer. So this map being injective is just a property of Z0, which we will see. And now the problem with this is this criterion is very strong. So, but this criterion is very strong. So what do I mean by this? So, for example, if we take the case of divisors, then the semiregularity map is just the boundary map from the short exact sequence and now here we can check that using Riemann rock. There are several examples. Of Z0 which are not semi-regular. So Z0 and X0. So the resulting map is not going to be semi-regular, but gives a positive answer to the question. Meaning that for all infinitesimal deformations of X0, we will get that the Hodge class remains a Hodge class if and only if Z0 lives as a local complete intersection. So now the question is that whether we can slightly weaken the criterion. So for this, we look at the semiregularity map a bit more closely, and we see where the problem lies or how subtle the problem is. So the semiregularity map. This thing comes in the following way. So first, I take x naught, then I cover x naught, open affine set such that in this open set, this thing is a complete intersection. Defined by, say, now using this, what we do is that we can further cover UI by more open sets. So this covering is for each UI. Now here I am going to use some local cohomology. So I just briefly recall the definition. So digression to local cohomology. So here what we need is, so here is the general situation. If we have a topological space and we take closed subscheme, closed subspace, here I can, and if I have F sheaf of abelian groups, here I can define the global sections of F with support in Y. Now one can observe that this is a left exact functor. And we define this HIYF to be the right derived, associated right derived functor. And similarly, one can do this whole thing on the level of sheaves, where I can define similarly, I just put an underline, to be on an open set U, I define this to be and get the sheaf and again this is going to be left exact And similarly, we can define the local cohomology. So this is the local cohomology group. And similarly, we can define the local cohomology sheaf. So now we can again continue with defining the semiregularity map. So here I had defined the equations. So what I do is as follows. So I take the differential form I take this differential form, and this gives a closed form in now using this I can define go to the cohomology class of Z naught in the following way. So this defines so first here I have defined it on just on UI. So this object is in so this object is in here. Now for p greater than equal to 1, this is going to be isomorphic to for p greater than 1. And for p equal to 1, we will have the class in the image. So here this object is defining an element in here. So now I want to see the image in the local cohomology sheaf. So here I will have where J is just this isomorphism comes from this theory of local cohomology, and this also. Any questions? Now the important point is these elements in here glue to give a global section here. The sections glue to give an element. Now here we are very close because you see the cohomology class of Z naught lies in the straight HP of omega x naught p. Now there is a natural map from here to that object which we will just see. So now a small exercise in this local cohomology tells us that you need locally free. You'll have the H naught of HP Z naught is just isomorphic to H. So this can be seen using a spectral sequence. Now the important point to note here is that if instead of 0 I had some I and here I had a J, such that I plus J is equal to P, but I is greater than 0, which will mean that this has to be less than P, then this thing will vanish, which will mean that the whole thing will vanish. So by the spectral sequence calculation, we will see that this is isomorphic to this object. Now from here we know that there is a natural map from this object to what we are interested in. So the theorem, this was, I don't know who proved this, but the cohomology class Z naught, which is the Hodge class in here, is just the image of this object. The image of under the map Now the point is that this, how close are we to answering the question? The point is that what we can show is for, if we ask the same question, not for the cohomology class of Z naught, but for this object, we will always get a positive answer. So what do I mean by this? for all t in T naught B such that the cup product of rho T union of this object. Now this object is in H naught of this. It's in here. So when you take the cup product, this is going to be in here. H of 1, and here 1 decreases. Z naught lifts as a local complete intersection for the corresponding infinitesimal deformation of X naught. So the point here is again showing the importance of the semiregularity map. So the semiregularity map so here I will define it from H1 so the semiregularity map is defined in this way. Then here I have HP plus 1 of P minus 1. And this map, so what this map is we know. So this map is defined in this following way. So there is a natural inner product map from, so here I write it using this thing. So this inner product map I will not elaborate, but it is very natural. So using the morphism, so this is the map we know from algebraic geometry. So using this map, we can define a natural inner product map. And if you take the H1 of this inner product map, you get the map here. So here we have H1 of this object. So what we see here is that so everything behaves well till here, and this is the map which creates all the problem. So I just elaborate on the proof of this statement so that we have some idea. So this is So what we do here is this. So we take I do it in the simple case. We take the case when V is an open subscheme or subset of a Hilbert scheme. And here we have that so subset of a Hilbert scheme parameterizing smooth projective varieties with some Hilbert polynomial. And we take that the smooth projective varieties are all embedded in Pn. So P and N are fixed throughout the whole of B. So in this case, it is quite simple. So first we consider we have the normal short exact sequence. And we have the sequence coming from the semiregularity map, which is again so this is the normal short exact sequence. And here there is a co-kernel. I do not care much what is a co-kernel. So here we have a isomorphism. Here we have an inclusion, which induces a map here. Let's say beta. And now, what are the maps here? So let's call this one alpha. So this is alpha. And this is, we know this one from the normal short exact sequence. So now the snake lemma tells us that beta is injective and we have, so now here there is going to be, the co-kernel of this map is going to be, and then again by snake lemma, which means that here I will again have surjective. The co-kernel again will be isomorphic to this object. So we get this diagram. Now the point here is this short exact sequence is split, which will mean that this one will split. So if I call the middle short exact sequence as, say, so as the vertical short exact sequence splits, so does this one. Now what does this mean? This means that if I take the global section of this object and the global section of this object, we will have a surjective map that is directly from the splitting argument. Now, which then means that we will have an injective map from H1 of this to the H1 of this object. So this implies the is injective. So now what we want to prove that the statement is here. So we want to prove that whenever I have this thing goes to 0, I have z naught left. So we can write this thing a bit more clearly. So what is this map? So I have a map from now this map I define in this way. I take a t here and I a product with this object. Now here we have seen we have not seen this, so I will recall this. So we have a natural map from here to, so what is this map? So this comes from, so you have a map from T0b, which is to H1 of Tx, that one we know. And from here there is a map to H1 of, and this comes from the short exact sequence. Sorry. So here I have skipped a step, so I will first need a restriction map. Here I have a restriction map. And here we have the map. Now, the result of Bloch tells us that Z naught lifts as a local complete intersection in x naught prime corresponding to an object in here to some t in t naught b. If and only if the image of T under this map it goes to 0. So call this map if and only if now here we have a starting point. Now this map is just what we have there. And the commutativity of this diagram is the result due to Bloch again. Now it is not very hard to show that since B is an open subset of the Hilbert scheme of smooth projective varieties, it has to be of the form, the tangent space is always of the form then there is a natural restriction map. And we have this map, which is coming from this, the long exact sequence associated to this normal short exact sequence. So this map commute, this is not very hard to show. Now, what we want to prove is the kernel of this map is this. So after this theorem of Bloch, we want to prove the kernel of this map coincides with the kernel of this map. That if we can prove that, we are done. Now, here from this normal short exact sequence, we have a map from here to here, and the object over here is exactly the missing piece. So let's call this a, this one I think I called alpha. So this one I call H1 of alpha. And call this part is exact. This horizontal part is exact. And we know that the kernel, so the kernel of this one and the kernel of this object intersects trivially. That is what we got here. So here we see that this map is injective, which just tells us that the kernel here is 0. Let's make this 1. So this implies that the now, what does that mean? So the kernel of this object is the same as the image of this object. Meaning that if there is any object here which goes to something, so this map factors through here. So meaning that it comes here, that has to go to 0 here because this thing is exact, which means that it has to go to 0 here. If whatever comes here has to go to 0 here. So I write this down. By the exactness of the bottom horizontal sequence, we have H1 of Z0. This map, when I restrict this, to the image of alpha naught is injective. Which implies this remark. Because then the kernel of the thing over here is the same as the kernel of this object, and here we see that the kernel of this object parameterizes all the infinitesimal deformations of x naught for which z naught lives, which means that so this is what we have written here. Now the question is that does this always happen? Of course not. So the point is, this is the tricky part of this map, that this map creates all the problem. So there are, of course, there will be cohomology classes for which the Hodge class lifts, but Z naught does not lift as a local complete intersection. So a criterion for this is the criterion when things behave well, which gives a positive answer to our question is, so this is what we have proven so far. Now, using Lefschetz 1-1 theorem, we can see that gamma lifts, or gamma naught, lifts as a local, as a Hodge class, if and only if the line bundle, the invertible sheaf lifts. As an invertible sheaf. Now, this means that there exists an invertible sheaf on pi inverse of the Hodge locus. So remember, this was the map for the family. So there is a invertible sheaf on this map such that when I restrict L to x naught, it's just, so the criterion when we have a positive answer is if there exists an open neighborhood U of x naught such that for all U in U, the global section does not jump. So now we have translated the problem into the jumping locus of the dimension of the linear system. So H naught of L restricted to XU is the same as when you restrict it to x naught, then for all P in Z naught lifts as a local complete intersection. So this is in the case of divisors. In the case P equal to 1. And we can also show that this is sharp. So there exists families when the H naught of LU jumps, meaning that it is not the same as H naught of at that point. And in this we get a negative answer. We can construct a concrete example which will give a negative answer to our question. So this is how far we have shown for the case of divisors. The criterion seems to be that the H0 of the linear system should not jump.